Welcome to the GetInsight podcast, powered by artificial intelligence and created for educational purposes.
Thanks for having me. I'm really looking forward to this one.
Yeah, me too. So let's just jump right into it. Imagine you are lying on an operating table mid-surgery. The surgeon is still working, making these, final, precise movements.
Right, the procedure is still fully underway.
Exactly. And the traditional approach in modern medicine is to keep a steady, heavy flow of anesthetic gas just pumping into your lungs right up until the very last stitch is sewn. But what if the anesthesiologist looked at their monitor and simply turned the gas off 20 minutes early?
I mean, it sounds incredibly risky, right? Especially if you are accustomed to the standard linear philosophy of acute care. We are deeply conditioned to believe that you turn a dial up and you get a continuous immediate response.
Right.
You stop the intervention and the effect stops. But turning off the vaporizer while the surgery is still ongoing is, well, it's actually the pinnacle of modern physiological control.
And that level of control is really at the heart of our deep dive today. We are exploring a technique called low-flow anesthesia. And, this is not just a minor adjustment to some dials on a machine. It is a complete paradigm shift in how we approach keeping a patient asleep. We're moving away from that linear input equals output mindset and entering into a dynamic, highly interactive biological ecosystem.
It really is an ecosystem. When you drop below 1 liter per minute mark, you are providing less fresh gas than the volume the patient is actually breathing per minute.
Which means the system has to compensate somehow.
Exactly. It becomes a semi-closed loop. The patient and the machine are no longer separate. They are continuously exchanging gases, recycling the same air back and forth.
Right. And to understand how doing less actually requires the clinician to understand so much more, we first need to look at the basic vocabulary used to navigate this closed loop. We are dealing with 3 critical acronyms today: FD, FI, and FET.
Yeah, these 3 measurements are they're the core language of the breathing circuit. Let's begin with FD, which stands for fraction delivered. This is simply the physical setting on the vaporizer.
It's the intention.
Exactly. It is the clinician's intention.
Yeah.
If you turn the dial to deliver 2% of an anesthetic agent, your FD is 2%. In a traditional high-flow system, what you dial is exactly what goes into the patient.
But in low-flow anesthesia, because the system is a recycled loop, that direct relationship kind of breaks down.
It does.
And that brings us to FI, or fraction inspired. This is the actual concentration of gas that physically enters the patient's airway. In a low-flow setup, your FI absolutely does not equal your FD.
Right, because the recycling creates a really complex mixture. When the patient exhales, that breath contains unused oxygen, unused anesthetic gas, and a high concentration of carbon dioxide.
Which you obviously can't just breathe right back in.
Exactly. So the machine captures that exhaled breath and forces it through a chemical scrubber, usually a canister filled with a base, like calcium hydroxide. That chemical actively binds to the carbon dioxide, trapping it and neutralizing it.
So it essentially cleans the exhaust. The carbon dioxide is stripped away, but the unused oxygen and the, expensive anesthetic gas are allowed to pass through, and they are sent right back to the patient to be inhaled again.
Yeah, that's spot on.
Okay, let's unpack this with a sort of analogy. It is a lot like ordering food at a restaurant. Your FD, the fraction delivered, is what you confidently ordered off the menu. But the FI, the fraction inspired, is what the kitchen actually puts on your plate, because they are constantly mixing your fresh order with leftover recycled ingredients.
I like that. The mathematics of the circuit align perfectly with that analogy. You are blending a tiny stream of fresh gas with a massive volume of recycled gas.
Right.
But the clinician also needs to know the result of that meal, which brings us to FET, the end tidal concentration.
Okay.
This is the concentration of the gas measured at the very end of the patient's exhalation.
So FET is basically the review you leave after eating. It tells the clinician what actually happened inside the body.
That's a great way to put it. Clinically, FET is the most vital number on the basic monitor because it serves as a real-time proxy for the alveolar concentration.
Meaning what's actually in the lungs.
Right. It tells the anesthesiologist what mixture of gas is sitting deep inside the microscopic air sacs of the lungs, right at the boundary where the gas diffuses into the bloodstream.
So FD is the intention, FI is the recycled reality, and FET is the physiological response. But knowing that FI doesn't equal FD only tells us that a disconnect exists. To understand how to manage the system safely, we have to look at the physics causing that disconnect, which brings us to the dilution effect.
Yet the dilution effect dictates the pace of the entire operation. Imagine a traditional high-flow anesthesia system as a small glass of water. If you drop a single drop of dark blue dye into that small glass, the entire volume of water changes color almost instantly.
Right, the system responds to your input immediately.
Exactly. But low-flow anesthesia is not a small glass of water. It is a swimming pool.
Wow, okay.
When you have a highly recycled system, the physical volume inside the machine's internal canisters, the corrugated breathing tubes, and the patient's own lungs adds up to a surprisingly large space, often several liters.
And into that massive volume, you're only introducing a tiny trickle of fresh gas, maybe half a liter per minute.
Exactly. So when a clinician turns the dial on the vaporizer to change the FD, it takes a significant amount of time for that tiny trickle of new gas to mix into the larger recycled volume, dilute, and eventually alter the FI.
The circuit physically holds onto the old gas concentration. It creates this stubborn lag that clinicians call system memory. The machine remembers what the settings were 10 minutes ago and slowly blends that past state with the new intention.
That's exactly what's happening.
Wait, if I put myself in the shoes of a clinician, relying on a system with a long, slow memory sounds genuinely terrifying. If a patient's blood pressure suddenly plummets and you need to wake them up to relieve the stress on their heart, or if they start showing signs of waking up in the middle of an incision, you don't have time for swimming pool to slowly change color. How do you manage an acute crisis when your machine inherently operates on a delay?
That is the critical question. If the patient requires an immediate drastic change in anesthetic depth, the low-flow state must be abandoned. The clinician will aggressively crank up the fresh gas flow to 5 or 10 liters per minute, physically overriding the system memory and flushing the entire circuit with new gas.
Okay, so you just flood the system.
Right. But your concern highlights why low flow requires such vigilant attention. However, there is a much slower invisible danger that system memory creates. And it doesn't involve sudden emergencies. It involves the silent formation of hypoxic mixtures.
Hypoxic meaning dangerously low oxygen levels, right?
Yes. Because the system is recycling the same air over and over, the gases within that loop are not static. The patient is a living, metabolizing organism. They are constantly consuming the oxygen out of the mixture to stay alive, while the anesthetic gas mostly just dissolves into the blood without being heavily metabolized.
Oh, I see.
So over time, the oxygen in that recycled loop is depleted far faster than the other components.
So if your fresh gas flow is incredibly low, the overall concentration of oxygen in that swimming pool can drift downwards, degree by degree, completely invisibly.
Yes, exactly. Historically, the primary defense against this invisible drift was a passive alarm system. If the oxygen concentration inside the circuit dropped below a critical threshold, a loud bell would ring, and the human clinician would have to assess the situation, manually reach over, turn up the oxygen dial, and wait for the dilution effect to slowly correct the imbalance.
Which places a tremendous burden on human attention. I mean, in an operating room environment where multiple monitors are beeping and alarm fatigue is a documented systemic risk, relying on a human being to manually fix an invisible gas drift is a pretty fragile safety net.
It really is.
Yeah.
And this is where modern medical engineering addresses the specific vulnerabilities of physics. The source material highlights the flow family of anesthesia systems developed by GetInsight.
Right.
They recognize that passive alarms are simply insufficient for dynamic closed-loop systems, so they integrated an active algorithmic safety layer known as O2 Guard.
O2 Guard fundamentally changes the relationship between the machine and the human. It constantly actively monitors the FiO2, the exact fraction of inspired oxygen that the patient is about to pull into their lungs on the very next breath.
And if that FiO2 falls below 21%, which is the baseline concentration of oxygen in normal room air, the GetInsight system does not simply sound an alarm and wait for intervention. It takes autonomous control.
Oh, wow.
It instantly overrides the clinician's current settings and injects fresh, pressurized oxygen directly into the circuit.
So it restores safe breathing levels immediately, completely bypassing human reaction time. This is a massive philosophical shift.
Yeah.
We are moving from reactive human monitoring, where a machine points out a problem and hopes the human fixes it fast enough, to proactive machine safeguards.
Exactly.
The machine is actively managing the dilution effects so the clinician can focus on the patient.
Right. Okay, so the machine can automatically inject oxygen if levels drop dangerously low. But how does the physical hardware actually measure and control these tiny recycled puffs of air without them just getting lost in the elasticity of the machine?
Yeah, that physical control has historically been the biggest engineering hurdle. For decades, anesthesia breathing circuits relied heavily on compliant reservoir bags. If you have ever seen an old medical drama, it is that stretchy, rubber-like bag that visibly expands and contracts as the patient breathes.
Sure. Yeah, the compliant bag acts as a temporary holding area for the exhaled gas between breaths. But the fundamental flaw with a compliant bag in a low-flow system is its elasticity. As the pressure inside the circuit fluctuates, the rubber stretches and deforms. Therefore, the volume of gas it holds is never entirely fixed or mathematically predictable.
Here's where it gets really interesting. Trying to use a compliant, stretchy bag to measure highly precise amounts of recycled gas is like trying to measure an exact cup of flour inside a thin party balloon.
That's a perfect visual.
Right, as you push the flour in, the balloon changes shape, the internal pressure shifts, and you are ultimately just guessing how much is actually in there.
Exactly. To achieve true low-flow precision, you have to eliminate the guesswork. Getting Gay's engineering solution to this is the volume reflector. They replaced the stretchy, unpredictable rubber with a completely rigid structure.
Okay.
Think of the volume reflector as a solid metal measuring cup. Because it cannot stretch or deform under pressure, it acts as a mathematically fixed volume chamber.
It stores the patient's exhaled gas and pushes it back into the breathing loop without any physical distortion. You know the exact millimeter of volume moving back and forth, but a rigid, opaque chamber presents a new problem, doesn't it? It is essentially a black box. The clinician can't physically see the bag inflating or deflating to gauge the volume.
Right, and precision requires visibility. A rigid chamber is useless if the clinician doesn't know what is happening inside it. This is why the physical hardware is paired with a digital interface called the Volume Reflector Indicator, or the VRI.
The VRI is essentially a real-time digital dashboard that gives the anesthesiologist X-ray vision into that rigid box. It visually dissects every single breath the patient takes, showing exactly how much of the current tidal volume is being supplied by newly added fresh gas and exactly how much is being drawn from the recycled reserves in the reflector.
And crucially, the VRI also visually indicates when excess gas is overflowing the chamber. When the system is too full, that excess gas is pushed out of the circuit and wasted into the hospital's scavenging system, the exhaust pipes that safely vent the gases out of the building.
Got it.
By monitoring the VRI, a clinician can dial down the fresh gas flow right to the absolute edge of what the patient requires, minimizing waste without crossing over into hypoxic danger.
So we have a rigid chamber for physical precision and a digital VRI dashboard for complete visibility. The breathing circuit is perfectly optimized, but here is the ultimate twist of this entire deep dive. Perfectly controlling the mechanical circuit is not the actual goal of anesthesia.
Not at all. The circuit is merely the delivery mechanism. The true target is the patient's central nervous system.
And to understand that, we have to journey beyond the mechanical lungs of the machine and step into complex human physiology, because there is a massive physical delay between the gas we measure in the circuit and the actual loss of consciousness in the brain.
To bridge that physiological gap, modern systems utilize a model estimate known as MacBrain.
MacBrain, okay.
Yeah. To understand why MacBrain is necessary, follow the physical journey of a single anesthetic molecule. When we measure FET, we are measuring the gas in the alveoli, but the lungs themselves do not experience anesthesia.
Right, the gas has to physically diffuse across the lung membrane and dissolve into the bloodstream. From there, it has to be pumped by the heart, travel through the circulatory system, reach the blood-brain barrier, cross over into the actual brain tissue, and finally bind to the neural receptors. That journey takes physical time.
It creates a significant temporal lag. If you rapidly increase the FI, the brain does not instantly fall asleep deeper. FET only reflects the lung boundary. MacBrain, however, is a sophisticated software algorithm.
So it predicts it.
Exactly. It takes the patient's age, their physical weight, and continuous exhalation data, and runs it through complex pharmacokinetic equations to mathematically predict the actual concentration at the target site, the brain. It attempts to give the clinician a real-time leading indicator of consciousness.
But that journey from the lungs to the brain is not a straight, empty highway. The blood passes by a lot of other real estate along the way. And this introduces a physiological phenomenon that completely dictates how anesthesiologists plan their procedures. hysteresis?
Hysteresis is a fundamental concept in physics describing a system whose current state is dependent on its past history. In low-flow anesthesia, it specifically describes the asymmetry of how anesthetic gases move through the body.
Meaning going in is different from coming out?
Precisely. The biological process of washing the drug into the body is entirely different from the process of washing it out.
When you first start delivering the gas, the wash-in phase, the anesthetic enters the bloodstream and heads for the brain. But it has to pass by fat tissue, muscle tissue, and internal organs. And those tissues act like dry sponges. They act as sinks, physically absorbing a large portion of the anesthetic gas out of the blood.
They steal the gas from circulation, which actively slows down the rate at which the concentration can rise in the brain. The body naturally resists the onset of deep anesthesia because these peripheral tissues are soaking up the drug.
Let me get this straight. The patient's own fat and muscle basically steal the anesthetic on the way in and then leak it back into the bloodstream on the way out. Because if the fat and muscle cells are constantly stealing the anesthetic on the way in, what happens at the end of the surgery? When the clinician turns the vaporizer off, the lungs start clearing the gas and the blood concentration drops. But those fat cells are still packed full of the anesthesia they absorbed over the last 3 hours. Doesn't that make the wake-up process incredibly unpredictable?
It would be unpredictable if we didn't understand hysteresis, because the blood concentration is now lower than the tissue concentration. The physical gradient reverses. Those fat and muscle tissues transform from being sinks into being sources.
Oh, wow.
They begin slowly leaking the stored anesthetic gas back into the bloodstream.
So on the way in, they slow the process down by absorbing the drug. On the way out, they leak it back into the blood, effectively keeping the patient asleep, even though the anesthesia machine has been turned completely off.
And this asymmetric leaking is the exact physiological mechanism that allows for the ultimate clinical payoff of low-flow anesthesia, the art of coasting.
Coasting completely upends how we think about finishing a procedure. If you are nearing the end of a surgery, the traditional approach is to keep the gas flowing until the final bandage is applied, then rapidly flush the system with fresh oxygen to force the patient awake.
But a clinician using coasting relies on MAC brain and their understanding of hysteresis. Significant minutes before the surgeon is finished, they turn the vaporizer dial to 0. However, they do not flush the circuit. They intentionally maintain the low-flow, closed-loop state.
So what does this all mean? It is the exact physiological equivalent of driving a car and seeing a red light 3 blocks ahead. You don't keep your foot slammed on the gas pedal until the very last second and then slam on the brakes. You take your foot off the gas early, and you let the mass and momentum of the car carry you smoothly to a stop.
That's a perfect way to visualize it. The patient's own body mass is that momentum. The fat and muscle tissues acting as sources gradually release their stored anesthetic into the blood. The closed circuit prevents that gas from escaping too quickly. This keeps the brain perfectly anesthetized for the final suturing without the machine delivering a single new drop of liquid agent.
You are literally using the patient's biological echo to finish the surgery. And the real-world impact of coasting and low-flow techniques is summarized by what our sources call the triple bottom line clinical outcomes: economy, ecology.
Let's break that down. Looking at clinical outcomes, by avoiding abrupt changes in coasting on the body's natural tissue release, the emergence from anesthesia is remarkably smoother. The body clears the drug at its own physiological pace, leading to a much more stable wake-up for the nervous system.
And if you are ever the one lying on that operating table, a stable, gentle wake-up is exactly what you want. But as a citizen, you also care about the economy. Because you are relying on recycled gas and tissue stores rather than constantly burning fresh liquid anesthetic, the physical amount of drug consumed plummets. We're talking about reducing drug usage by over 50% in some cases, saving healthcare systems massive amounts of money.
Absolutely. And that reduced consumption directly drives the third, arguably most vital pillar: ecology. The volatile fluorinated ethers used in modern anesthesia, like desflurane and sevoflurane, are extraordinarily potent greenhouse gases.
When a traditional high-flow system vents unused gas into the hospital scavenging system, it goes straight up a pipe and into the atmosphere. Running a traditional anesthetic case for 1 hour can have the same global warming impact as driving a car for hundreds of miles.
By heavily restricting the fresh gas flow, trapping the gas in a rigid volume reflector, and coasting at the end of the procedure, clinicians drastically cut the volume of these potent chemicals being exhausted into the sky. It is a rare alignment where optimizing the physics for the patient simultaneously protects the planet.
Low-flow anesthesia challenges us to realize that doing less requires an immense understanding of the whole picture. It forces the clinician to integrate the physics of the dilution effect, the rigid precision of a volume reflector, the algorithmic foresight of MacBrain, and the biological reality of hysteresis into one cohesive strategy.
It completely redefines the relationship between the machine and the human body. They are no longer separate entities. They are partners in a dynamic ecosystem.
We have covered incredible ground today, but we want to leave you with one final thought to mull over. If the principle of hysteresis, this asymmetric biological storage where tissues act as sinks and then sources, governs how inhaled gases behave so fundamentally, where else in medicine is this exact same principle quietly operating?
Think about the broader landscape of pharmacokinetics. Think about a patient on a long-term course of intravenous antibiotics or heavy pain medications or psychiatric drugs. How are those complex molecules hiding in the patient's fat and muscle tissue over weeks or months?
And the truly provocative question is, what would the equivalent of coasting look like in those fields? Can we design long-term treatment plans that intentionally utilize the body's own stored momentum rather than just continuously pushing more drugs into the system?
It's just a future where medicine is less about overwhelming the body and more about navigating its natural currents.
It changes everything about what it means to heal. Thank you for joining us on this deep dive today. We will catch you next time.